Hi, I am Sanjay Patel. In today's lecture, we are going to introduce the concept of quotient ring. The concept of quotient ring is similar to that of the concept of quotient group, what we have done in group theory. So before we start, let us recall some of the important ideas and concepts from the quotient group. Suppose G is a group with respect to some binary operation star, okay, and say H is a subgroup. H is a subgroup of the group G. You know what is a subgroup? It is a non-empty subset of a group which is itself a group. Okay. Then we define two special sets in G which are known as cosets. So you recall the definition of cosets. We have defined two types of cosets in group theory. If H is a subgroup of the group G, and if we have, say, a subgroup H and an element A in the group G, then we can define a set which is denoted by the symbol H in HA, and the meaning of this symbol is the set of all the elements of the form H star A, where small h belongs to capital H. So that means we have to multiply all the elements of the subgroup H on the left hand side of the fixed element A. Then set of all such elements is denoted by the set HA, and this is known as left coset. Sorry, it is known as right coset. This is called right coset of element of H, right coset of H by the element A in the group G. Remember, this thing is a subset of the set G. Okay, same way we can define what is called left coset. Here A is written on the right hand side of H, so it is called right coset. And if it is written on the left hand side of H, we know it is called left coset. So the definition is just replacing H star A by A star H. So this is called left coset of the subgroup H by the element A in G. So we know this type of cosets, and remember here star is any binary operation. So if you take different groups, then this operation are different. And just note that if the operation star is addition operation in any group, not necessarily addition of numbers, it can be addition of matrices or addition of polynomials or whatever. So if star is the operation of addition, then we write the symbol HA, this HA we write as H plus A, and we write the symbol AH, the left coset symbol, we denote it by A plus H. So just for your information, that for operation of addition, the left coset and right cosets are denoted by the symbols A plus H and H plus A respectively. Okay, and we know that this, for a given element A in the group G, the left coset and the right coset, these two are different sets. They may or may not be equal. Okay, if they are equal for every A belongs to G, then we know that H is called a normal subgroup. Normal subgroup of the group G. So it is our definition of a normal subgroup, that if H is a group, or if H is a subgroup of a group G, and every left coset is equal to right coset, then the subgroup is said to be a normal subgroup. So it is a very, very important concept of normal subgroup in a group theory. And we are going to introduce a similar concept here. But before that, just again recall that if G is a commutative group, if G star is a commutative group, you know what is the meaning of commutative group? It means the operation star is commutative, that is A star B is same as B star A for every A and B belongs to G, then every subgroup of the group G is always normal, subgroup. Okay, so this is very important remark which I am going to use in extending the concept of quotient group to quotient ring. If every subgroup in a commutative group is always normal. The reason is, in this case, these two cosets are always equal because H star A is same as A star H for every element in the group, because H is a subset of G, so every element of capital H is also an element of G, hence HA is equal to AH is always true. So in a commutative group, every subgroup is always normal. Now let us consider a similar thing in case of ring. So now about ring theory. In ring, say R plus dot, let me take any ring R plus dot. If I consider an ideal, let capital I be any ideal in R. Okay, you know what is an ideal? Ideal is a subset of the ring which has two properties. First of all, that I plus is a subgroup of R plus. That was our first condition, and the second condition was the ideal condition, that for every X belongs to I and for every R belongs to capital R, we have X into R belongs to I and R into X also belongs to I. So this is our definition of ideal. What I want is only this first condition. If I is any ideal in the ring R, then I plus is always a subgroup of the group R plus. But in the ring R, we know that the operation of addition, that is plus, is always commutative. So if R is a commutative group, then every subgroup of R with respect to addition is always a normal subgroup. So this I plus must be a normal subgroup. So I can write an important conclusion from this discussion. Since R plus is commutative group, the subgroup I plus is a normal subgroup, of R plus. What is the meaning of this? The meaning of this is we have every left coset of I is same as right coset of I in R. So that implies I can write IA is equal to AI, HA is equal to AH for every A belongs to R. But here operation is plus, so we are not going to write this notation. We are going to write the notation I plus A is equal to A plus I for every A belongs to R. So remember, if I is an ideal in the ring, then that ideal is always a normal subgroup of the group R. So therefore, I in ideal, let me write this way. Therefore, every ideal in ring is a normal subgroup, of the group R plus, is a normal subgroup of R plus. Okay, so this is a very, very important observation, and just for your say reference and understanding, let me also rewrite the meaning of I plus A. Just note that note that I plus A means elements of the form small x plus A where x belongs to I. Okay, and A plus I is set of all elements of the form A plus x where x belongs to I. Here I is something like a subgroup, and here A is any element of the ring R. Remember, A belongs to R here. Okay, that is one thing. And now let us recall the meaning of quotient group. What is a quotient group? For defining a quotient group, we take a normal subgroup of the group G. So we always start like this. Let H be a normal subgroup, be a normal subgroup of a group G comma star. Whenever we have a normal subgroup, we can collect all the possible distinct right cosets of H in G. Remember, all the right cosets and left cosets are equal. So you can consider any type of cosets, whether left or right is not important in this case. So what we define in this case is the set of all possible distinct, say, right cosets or left cosets, both are same, of H, of the subgroup H in G is called a quotient group. Is called a quotient group, and it is denoted by the symbol G oblique H. Okay, G mod H. So just for the clarity, the quotient group is nothing but set of all elements of the form HA for different A belong to G, and here we consider only distinct cosets. Okay, and this set itself is a group. This set itself is a group with respect to the operation defined in this new set, and we know how it is defined. For HA and HP, any two elements in G mod H, that is B belong to G mod H, we have defined HA into HB. So multiplication of, or you can say HA star, or let me use the operation dot only, or any operation or any symbol you can use, say plus circle or anything. HA plus circle HB is actually HA star B, but we are not using different notations here. What we are doing is we simply write the same notation, and it will be clear from the context where the operation is written. Something like HA dot HB, and if I write here HA into B, you note that this dot is between the two elements A and B, where A and B belongs to the ring R. So this A into B is a multiplication of the ring R, and here HA dot HB means this operation is our definition of binary operation in the set G mod H. Okay, so it is written between the two cosets, so it is called multiplication of cosets. This is written between the two elements of the ring, so it is multiplication of elements in the ring. Okay, so this is about say quotient group, and we want to define exactly same thing for a ring. So here what I am going to call it as a quotient ring, and we already discussed that every ideal in a every ideal in a ring is always a normal subgroup of the ring. So now the definition of quotient ring. Definition of quotient ring. let R plus dot be a ring. Okay, and capital I be an ideal in the ring R. Capital I be an ideal in the ring R. Okay. Then the set of all possible right cosets, set of all possible distinct right cosets, distinct right cosets of I in R plus is denoted by, this set is denoted by the symbol R oblique I, that is R mod I, and is called the quotient ring. Is called the quotient ring. Okay. So this is our definition of quotient ring. So just we write the meaning of R mod I in the set form. R mod I is nothing but set of all elements of the form I plus A, where A belongs to R. So here I plus A is a right coset of the ideal I by the element A belongs to R. So this is something very important and will be useful in defining special type of ideal at the end of this course. Okay. So I plus A is a right coset of I in R. Okay. What is our next aim is to prove that R mod I is always a ring with respect to some two operations. So that two operations we'll define later on, but just to understand how this kind of set can be, say, constructed, let me give you a very simple example to understand what can be the set R mod I. Say, consider some ring. Say, consider the ring of, say, residue class is modulo 6, Z6 plus 6 dot 6. So here R is Z6. Okay. Now I consider another thing which is an ideal to define the quotient ring. So let some ideal, let me take I is equal to the ideal generated by, say, some element 3. Okay. So what will be this set? We know it is an ideal, but what are the elements of this set? Is ideal in the ring R. Okay. If you want to find this, we know the definition of this ideal, principal ideal is R into A. Here A is 3, where R belongs to R, that is Z6. And what are the elements of Z6? It is class 0, class 1, class 2 up to class 5. So you have to put R equal to 0, 1, 2, 3 and so on up to 5. So what I will get is, if you put R is equal to class 0, something like this, class 0 into class 3 and class 1 into class 3 and so on up to class 5 into class 3. Okay. So this gives us, if you find all values, and remember this dot is the multiplication operation of the ring Z6, and in Z6 the multiplication operation is dot 6. So 0 into 3 is 0, 1 into 3 is 3, 2 into 3 is 6, but 6 is equal to 0, so no need to write it again. Then 3 into 3, that is 9, or let me write all the elements just for your understanding. This is 6, then this is 9, 3 3s are 9, then 4 3s are 12, then what else? 5 3s are 15, and then finally, okay, that is 5 is the last element. So 1, 2, 3, 4, 5, 6. Fine. So these are the all possible multiplications you will get. But these are all not distinct. They are, some of them are equal. Like you can observe here that class 0, then class 6 is same as 0 because 6 modulo 6 is 0. I mean 6 is congruent to 0 modulo 6. Then 12 is also congruent to 0 modulo 6. And this 3 and this 9 and this 15 all are same. Class 3 is equal to class 9 is equal to class 15 because 9 is congruent to 3 mod 6. 15 is also congruent to 3 modulo 6. So in fact, we have only two distinct elements in this set I. So the ideal I generated by the element class 3 is the set containing only two residue classes. Now we are going to find all possible cosets of this ideal in Z6. So I consider now R again, that is Z6 is equal to class 0, class 1 up to class 5. Okay, and I is equal to the ideal containing only these two elements. Okay, so now we find the coset I plus A where A belongs to the ring R, that is Z6. So we start with the first one, A equal to 0. Let me write this way. If A is equal to 0, rather class 0 in Z6, then I plus 0 is equal to what? Just you have to add all the elements here. So we'll get same as I. You know the properties of cosets. Let me explain that quickly. We know this thing that say HE is equal to H is equal to EH, where E is identity element. Here 0 is identity element, so I plus 0 is equal to I. Okay, then we have, if A belongs to H, then HA is equal to H. Then we have, if A belongs to HB, then double implies HA is equal to HB. So these are very, very important properties of cosets what we have studied in group theory. Just keep in mind. So using this we can also obtain another right coset for the element A is equal to class 1 belongs to R. We have I plus class 1. What you to do is just keep on adding this element 1 with elements of this, because this means X plus class 1 such that X belongs to I. And this plus is our addition modulo 6, because in ring R, which is Z6 in this case, we have operation addition is the addition modulo 6. So we get 1 and 1 plus 3, that is 4. Okay. Again, if I take, say A is equal to 2 belongs to R, that is Z6, then I plus class 2, that is say X plus class 2, where X belongs to I, gives you, putting X equal to 0, 0 plus 2 is 2, and putting X equal to say 3, 3 plus 2 is 5. So we get these two sets, these two elements. Same way, if I take A is equal to class 3 belongs to Z6, then I plus class 3 is equal to I. Why? Because class 3 itself belongs to I. So I'm again using the result. If A belongs to H, then HA is equal to H. Here class 3 belongs to I, which is the given ideal. So this will be true. Next, for A is equal to 4, belongs to the ring, that is Z6, what I can find is I plus 4. I contains only two elements, class 0 and class 3. So class 0 plus class 4 is 4, and class 0 plus class 3 is class 7, and class 7 is equal to class 1. So I can write class 1 because 7 is congruent to 1 modulo 6. We have to mod out every element by 6. And finally, the last element in the ring, whose right coset for the given subgroup I is I plus 5. So again, 0 plus 5, that is 5, because I contains 0 and 5 only, 0 and 3 only. So class 0 plus class 5 is 5. Class 3 plus class 5, that is class 8, but class 8 is same as class 2, because 8 is congruent to 2 mod 6. So just observe that out of this, how many cosets are distinct. So this I here, we are getting here also I, okay. So these two are same. Then these two cosets are same. This and I plus 4, okay. And finally, class I plus class 2 is same as I plus class 5. So just note that we have I plus class 0 is equal to I plus class 3 is equal to I. Then I plus class 1. We have found that I plus class 1 or not? Yes, I plus class 1 is the set containing class 1 and class 4. Then I plus class 2 is the set containing I plus class 2 is 2 and 5. So class 2 and class 5, that is also distinct. And I plus class 3, that is same as this. Oh, that is written already. Okay. And all other cosets are say equal. I plus 1 is same as I plus I plus 1 is same as I plus 4. Then I plus 2 is same as I plus 5. Okay. So if you do like this, you will get only these three distinct cosets. So therefore the quotient ring R mod I is the set of all distinct cosets, that is I plus class 0, then I plus class 1 and I plus class 2, okay, which we can write as I plus class 1 and I plus class 2. So this set is actually a ring which we are going to prove in our next lecture, and this ring is known as quotient ring. We are going to prove the fact that for if any ideal I in the ring R mod I is always a ring. The quotient ring is always a ring with respect to two special binary operations which we are going to define there. So till then, goodbye and thank you.